Okay, good afternoon. My name is John Criswell, and today I'll be sharing a few thoughts on using Clang and LLVM for automated defense. So first, what do I mean by automated defense? I mean a compiler that can automatically generate executables that are already protected from one or more broad classes of security attacks. In this particular talk, I'll be talking about memory safety attacks because for C and C++ code, that's still a major problem. So I think automated defense is an important problem because I see trouble on the horizon. We are depending more and more on vulnerable computing devices. They're vulnerable because they have vulnerable software on them. Attackers are better funded and more motivated. Sadly, we can't fix all the bugs, partially because we have to find them and partially because we're continually adding new bugs with new code that we write. And so I think automated defenses can help defend us. Now, I suspect that there are other people in the LLVM community that agree with me because Clang already has automated defenses. Unfortunately, the automated defenses that it has are not very good. The two of which I know are stat canaries and partial bounds checks. Stat canaries are so easy to bypass that students at Johns Hopkins University are required to do so for one of their homework assignments. And partial bound checks, well, they actually work. Just to be clear on what they are, if the compiler can insert a fast bounds check at runtime, it does. Otherwise, there's no check at all. But it's not quite clear how much security you're getting. So what I suggest is the following. I suggest that we look at techniques that can give comprehensive security guarantees and decide, well, how much security do we want for the performance overhead that it provides. So at the bottom of the barrel, there's control flow integrity, which basically ensures that your indirect branches and your returns go to some address where they're supposed to go. And the fastest implementation of that, which is LLVM based, by the way, is 8%. If we want to worry about techniques that handle attacks that don't alter control flow, then we might want to look at write integrity testing, or safe code as described in the PLDI 2006 paper, which note the optimizations in that paper are not yet enabled in the default safe code compiler today. Those have 18 and 30% overheads respectively, and those basically ensure that your loads and stores only access a subset of correct memory objects. If we actually want to do bounds checking, where we make sure that pointers don't jump from one memory object into another, that'll be 68% overhead and softbound plus sets. If you want to go full board and make sure you don't have any dangling to pointer to references, that'd be 116. If you're interested in other memory safety techniques, I'd suggest looking at the Memory Safety Menagerie website given on the slide. So I think that given the danger that's lying ahead and the techniques that we now know how to do, it's time to move from research to practice. The first step in that is to stop trying to use weak security solutions. I don't see any point in implementing techniques that we know don't work. Secondly of all, I think we need to look at using the best of breed techniques. In research, there's a lot of different research papers. They have a lot of different techniques. We need to pick the best from each paper, if you will. Third, we need to have realistic discussions, which we started, I believe, in the BOF session earlier today, on security performance trade-offs. And then finally, we just basically need to build something, get it out to people, and see what they think, and see what they need. Thank you.